Yes.
Okay. I think some of what I'm going to be talking about here will also illustrate some of the concerns we have with events which are at the pushing the boundaries of about observability. Anyway, this is about stats and showing some results from this year. So I'll try to keep this relatively quick because I know I can waffle on. Here's a plot of the number of events recorded each year. As you can see, the numbers are continuing to go up. Now, why hasn't it got 2023? For some reason, I don't have the latest year. Well, anyway, the numbers keep on going up. This year is 2023 is more than 2022 and so on. I've got a sense the rate of increase is starting to decline a bit, but it's the volume of observations coming through are putting significant stress on everyone. The US system is really struggling. Japan is having trouble. Dave Galt is keeping his head above water. I'm not sure. He's okay, I think. And SODIS seems to be working very well in Europe, in part because they've got a whole heap of people involved with it. One of the things I regularly look at is what are the percentage of observations that come through where okay, we figure, yeah, this is a reliable result and we can report astrometry or whatever else from it. As you can see, if you go back to pre-2000, the reliability was, some years was pretty crap, to put it bluntly. But video started coming into place around about 2000, and there was some improvement around about 2007. I'm not sure whether that's when the VTI came into place. Dave's nodding his head there. And since then, the percentage of unreliable results has remained fairly constant at about 2 or 3% of things that come through. 2023 was more than 2022, but 2022 seems to be unusually low. This shows the by the regions, the number of events, total numbers, but also the number of events by asteroid diameter. And, well, that figure speaks for itself, I guess. Europe and North America are consistently high. 2023 and 2022, Australia has been surprisingly high given the small number of observers. And a lot of that comes from the small asteroid measurements. I think a major factor is that there's a significant number of Australian observers have a fixed telescope in some form of observatory, which makes it much easier just to go out and observe an event. I know there've been a couple of times when I've realised, oh, geez, there's an event coming up in a small number of minutes, and I can race outside, open up and get onto the target in less than 5 minutes. And that makes it much easier to observe heaps of events compared to if you've got to actually put your telescope together to observe. This is just indicates the total number of events by over a period of 23 years. Large number of events. Again, Australasia is surprisingly large number. This is an interesting plot. It shows the number of positive chords, so the number of events for different numbers of positive chords. The top line are single chord events. The very bottom line is for number of chords greater than 10. What you can see there is that the number of very well observed events, the blue line at the bottom, is still a very small number. It's increased, but not by a huge amount. The second bottom line, 4 to 9 chords, there's been a slow increase from about 2016, but it's a slow increase, and that requires, to get that number of chords, so almost certainly requires a major effort of multiple observers to go out and set up to observe an event. Green line, 2 to 3 chords. Interestingly, this last year had a small reduction in the number of those. It's grown significantly, but where the real growth is in single chord observations. And this is all about people with fixed telescopes permanently set up, being able to just go outside, turn the telescope on, observe an event, and then 20 minutes, half an hour later, just close it all down and go to bed. It's an observing convenience issue more than anything else. Yeah. Now, this is just an interesting plot here. The top left is the number of chords, a plot of the number of chords, same as the previous plot, by the regions. And the one below that is a similar plot from covering an earlier period, not a hugely different earlier period. But there is a fair degree of similarity of the number of chords by region across those years. But what's also quite interesting is the top right is getting rid of the absolute numbers and putting them in as a percentage. And what you can see here is a difference in the percentages of multiple chord observations versus single chord observations. Australia and South America have very, very, very few multiple chord, large numbers of multiple chord observations. At the other extreme, Japan has a very high percentage of 4 to 9 chords and more than 10 chords. The percentage is greater than any other region. And the reason for this is they have a fairly decent number of observers, but Japan is a relatively small landmass. So you've got a large number of fixed observatories in a small space. So when they do have an event, typically they have multiple observers. So if you're after multi-chord observations and to measure the diameters and shape of asteroids, in relative terms, Japan is streets ahead of everyone else. Top plot here is the average number of observers per event. If you go back to 2000, the average number was up about 7. That was in the days of visual observing and people going out to observe them, but the number of events was quite small. You can see that the number of observers per event has been slowly reducing over the years. So we're down to 2.0. This is nothing to do with observer numbers. That is all an effect of more single chord observations being made. So as you saw from the, I'll go up, from this plot, number of single chord observations have gone up, whereas the multiple chord observations haven't really gone up. But the effect of the increase in single observations means that there's far more events with just one observer, which is why that number is reducing. The bottom plot there shows the total number of observers for any event that's possible. Let's say a positive event. It jumps up, moves up and down a bit, but for the last 5 years, last 6 years, it's been basically it's a constant number, somewhere around a bit over 400 worldwide. If I think I remember correctly, SODIS has got over 200 observers listed in their system. Double stars. This separation of double stars is, we discover, is 1 to 100 milliarc seconds. That's basically, I think the only double star mentioned in the whole data set, where it's a known double star, is an occultation of Beta Scorpio back in the 1971 or something, where the components were quite wide. Every other double star which has been detected in asteroid occultation is otherwise an unknown double star. So if you have a double star detection in your light curve, you've made a discovery. It's as simple as that. The mathematics associated with it, depending on how many observers there are, it can be either a unique solution, 2 or 4 solutions, and the uncertainty can be quite small. Now, this is the list of double stars discovered last year. It is more than 2 times the length of any previous year. It's a significant increase in the number of double star discoveries. And several of those have come about when we've been adding results into the main database and we have the light curve readily available. Quick look at the light curve and we say, oh, there's a step in that light curve, small step, and the observer or whoever else has analysed it has failed to notice it. So that's one of the positive things we're getting out of having the light curves come through. We're actually detecting things which the observer hasn't recognised. We had one binary asteroid discovery last year, 5457 Queens. The top line gives the 3 light curves for observed from the first event, which is middle left. As you can see from the light curve from Jan Manek, you've got the main event and then you've got a very short drop to basically the same light level. It's consistent with the possibility of a satellite, and I'll be talking more about this issue this afternoon. But it's a very short event. There are issues about whether it was a real event or some sort of noise event. For that type of event, you need to carefully have a look at the light curve measurement to make sure there's been no tracking error in when the light curve is being measured. And we recently had a situation where that was the cause of a drop. And you also need to check multiple comparison stars to make sure the drop is unique. So on the basis of the light curve and doing the checks, it seemed to be a highly probable binary discovery. But Several weeks later, there was a second occultation of by that asteroid, which is the bottom one. Yes, the light curve is noisier, but the light drop is the same light level. Duration of the secondary is about the same. And a confirmation of the fact that that asteroid is binary, and that's been recorded in the CBET, Central Bureau of Electronic Telegrams. I should mention that was the third asteroid satellite discovery we've had published in the CBETs. That's full recognition. This year, there's another 3. In the first 2 months, we had 3 more satellite discoveries, which is a seriously significant thing. Now here I'll just go through a selection of events from the second half of this year. The most notable event was the Betelgeuse event, or Betelgeuse event. Clearly the best event of the year. That's a plot of all the chords of all 71 observers. There were no miss observers. As far as I'm aware, they were all successful. You can see that the uncertainty chords are generally quite large, but there's a good reason for that, which I'll show in the next slide. But a very good result for that. Now, one of the nice things about what we're doing now with light curves is there is the 67 light curves for this event. Now, you can cast your eye over all those light curves and see the significant variation in the I hesitate to use the term quality, but in an objective sense, the quality of the light curves in the sense of signal to noise ratios is significantly different, and you can see how many of those light curves are affected by cloud. But there's also another interesting thing you can see from these light curves, which will presumably get picked up in detailed analysis by professionals. The occulting asteroid Leona is elliptic. And depending on the inclination of the ellipticity to the motion of the path, the mid-time of the observed light curve will vary across the path. And I'll give a couple of examples here. If you look at this light curve here, you've got to look carefully. Look at that curve. It's a fairly well-defined curve, but the bottom of that curve is not exactly halfway between the two. The bottom of that curve is displaced that way. This light curve, the noise, there was a bit of a problem, but it's displaced that way. Up at the top right, that's clearly displaced to the left. And you can go through these, and I think this one's displaced to the right. That displacement is an indication of how far you are from the center path, center line of the occultation path. It's a type of information you can extract when you have the light curves available. But detailed analysis, getting precise event times, that's in that type of light curve, it's not a straightforward exercise, and the event times that we have large uncertainties because of the problems of identifying where the D and R properly is located, and things like limb darkening effects on the star. Now here's an event, Hilda, observed, I think, in Europe. Very large asteroid. It's 150, 180 kilometers diameter. a range of chords, large uncertainties, but you can sort of fit and ellipse through them. Question is what type of accuracy do you have it? It's clearly reduced accuracy compared to if you've got much shorter uncertainty chords. We have 3 light curves for this event. When you look at those, you can see the top 2 light curves are very definite. Then when you look at the bottom light curve, you sort of say, well, yeah, I think I can see the event there. But it raises question. Well, if you had that light curve reported with the same uncertainties as the top light curve, you would get rather concerned about how uncertainties have been determined. Here is another event. We have light curves for all 7 observers, which is useful to see. And it's interesting to look at these light curves. Bottom left one, yeah, where is the start and end of the occultation on that light curve? I haven't matched these ones to the chords in the event. I'm hoping that that light curve goes to that middle chord on the on that plot where it's got very large uncertainties, because the start and end of that light curve is anything but clearly defined. And you can look at all these light curves and ask yourself, which ones of those are you confident about whether or not it's a real occultation, or where does the start and end of the occultation? Now, this star has been reported as a double star, and that's on the basis of this light curve here, with a full dip there and a step event there. I just ask you to reflect upon, do you think that that is a step event or a noise event? And how can you be reasonably satisfied that it's one or the other? Now, it's interesting that only one observer identified the existence of a double star. And when you look at all the other light curves, are any of those other light curves capable of identifying a step event of the nature in that first light curve? And this is an example of some of the challenges we have with interpreting the results from an event. This is an interesting one with 2, 4, 5 light curves, 5 chords. The magnitude drop was 0.2. There are people that like observing really small magnitude drops. It's a gee whiz thing to do. I can, even though its magnitude drop is only 0.2 or 0.1, I can get reliable results from it. Well, this is a 0.2 magnitude drop. You can see the uncertainties, the reported uncertainties in the light curves. What sort of accuracy can you get from the astrometry from it? Seriously reduced. And can you derive anything useful about the shape of the asteroid? Very limited information. Then have a look at the bottom curve and look at the light curve. when you see that light curve, how confident are you about the start and end of the occultation? And yes, there are large uncertainties given on that occultation, on the chord. But I guess the question is the occultation somewhere in this region? Or what's this dip here? Hey, it's a very noisy event. You've got large dips over there. Is that just atmospheric effects involved in the whole light curve? The fact that it's similar to the adjacent light curve would give some support for it, for there being an occultation event there. But does that justify a clear disappearance and reappearance times of the event? Just how reliable is the whole event? It's a challenge. Here's a reasonably well observed event. And again, the uncertainties for this are quite significant. It's probably not, having the plotted on the black, the uncertainty regions aren't so great. Aren't so easy to see, but you can fit a circle of the assumed diameter of the asteroid to them, or you can fit an ellipse to those same chords with not much difference in the quality of the fit. So in that type of circumstance, large uncertainties, relatively large uncertainties, does it tell you anything about the shape and orientation of the asteroid? Not so well. It's limited information. Astrometry is probably okay, given the alignment of those chords. It's also interesting to look at the light curves in context. Bottom, like I've linked the light curves to the relevant chords here, and the bottom left light curve has a much lower resolution than the bottom right chord, and that's largely reflected in the increased uncertainties associated with those two chords. I guess the question is, how reliable are the uncertainties in that bottom left chord light curve, particularly on the reappearance side? And as a contrast to this, this is a nice observed event. You can see the chords have very small uncertainties, and they fit the shape model very nicely. You can see that there are well fitted around here and here. Significant difference in the shape model here. That bump on the shape model doesn't seem to exist. And the reason why all that occurs is when you look at the light curves, and this one, I'm not sure what happened to the generation of the light curve, but it's only the D part shown. But you can see you've got very well-defined disappearances and reappearances. They get reflected in the accuracy that you get in the fit of the shape model, a fit to the shape model. Another thing to note here, these two chords, the disappearance time for that chord is later than this chord, and the uncertainties of both those chords do not overlap. And if you look at the reappearance side, there is overlap, but that chord is displaced that way compared to that next chord. And this cannot be a real event here. I mean, that's not a possible physical feature of the asteroid. It all indicates that there is a time-based error with one, possibly both, but most likely one of those two chords. And this is not an unusual thing for us to see when we're pulling the final observations together. And where necessary, we'll, if that was observed, time-based was NTP, we'd just downweight that one or even exclude it potentially from the results. And I think that's all I wanted to say. Bye-bye. I think I finished early for once.
Well done, Dave.
Yeah. Questions?
Yeah, thank you very much for the talk. I've got a question in regards to Betelgeuse occultation. Do you have any comments to make in regards to larger airy disk than the asteroid?
I couldn't quite hear. You said something about airy disk?
Yeah, apparently the star there was a cult. Yeah, the Betelgeuse airy disk is actually larger than the asteroid's diameter. So, comments have you got for that?
Okay, I'll go back to that. You can see from these light curves that none of them go to zero light. And that's because Betelgeuse was great, had a larger diameter, apparent diameter, than the asteroid. This isn't an airy disk issue, which the airy disk, size of the airy disk is dependent on the telescope, the aperture of the telescope, and the occultation context. The airy disk is totally irrelevant. The factors for gradual light curves are star diameter and Fresnel diffraction. Star diameter, both in much smaller than the asteroid, where you'll get a full disappearance, but a gradual disappearance. If it's sort of equal to the asteroid diameter, you can get some interesting effects because you're dealing with annular occultations, or what I call bifurcated occultations. You can have the asteroid in the middle of the star, blocking off a line across the middle of the star with elements of the star appearing on either side of the asteroid. So you have two bits of light separated by a dark band. And then, as in this case, you have the star being larger than the asteroid. And when you get that, that's when you get effects like I was pointing out here, where the bottom of the light curve is displaced one way or another when you move away from the center line. The bottom of the light curve doesn't get to zero. And how little it drops or how much it drops depends on your distance from the center of the path, like in that one. And there's one up here, which I can't quite see on my screen, where there's hardly any drops, very small drops there, to something like here, which is a very large drop. Yeah. Does that answer your question?
Yeah, thank you very much. Much appreciated.
Yep.
I've got another question. I don't know if you can dial up different curves from our results of this year's occultations, but I had an interesting effect on what is it, 27th of February, when Annalise occulted a star, and I had a sharp drop off, and then it was almost a hyperbolical curve back up. Yeah.
Um,
I can take my laptop to the camera. Maybe you can see it.
which was it, Annalise?
Annalise, yeah.
Okay,
900.
I have the light curve for that, so I shall transfer that over onto
That's the one.
onto the shared screen.
It looks like mine, yes.
Yep, that's it there.
Yes.
Okay, well, let me just go back to, and there's another thing I need to move over. Okay, this is the light curve plot as Renato indicated. I've got your name right, haven't I? Sudden
that's
drop,
correct. Yes.
and then some sort of rise. You could suggest that it's a slow rise there or something, and not as steep a rise as there. And it's you got to be careful on. It's the fact that that point there is not down here, which makes that a gradual event. That one could be just a case of the reappearance occurring halfway through one exposure frame. But because that one's that much higher, there's a gradual event. The key thing here is to plot this against the actual expected side of the asteroid, which this it is. And you can see here that the observed chord is very much shorter than the expected diameter of the asteroid. So we can displace all this, and you can see that chord is clearly a grazing occultation event. And it's that factor which gives rise to that shaped light curve. The interesting question is, or the questions to ask there, and I'll go back to the event. Just bear with me a second. I'm not showing this on the screen. Stellar diameter. For this event, I'll bring this up on the screen anyway. This is a form you can bring up in Occult, and I'll bring it over to here. It gives details about the star, and the diameter of the star is estimated as 0.02 milliarc seconds, which is quite small. And because it's so small, you wouldn't expect to be seeing any fading effects by the because of the star's diameter. I'll just change something here. I've just added a line there, that dotted line, and that shows where the top of the diffraction pattern from Fresnel diffraction would occur. And you can see that if you've got a line across there, there'll be a period there where it's still rising in brightness, a slow rise there. And this issue here with Fresnel diffraction is the most likely explanation for what's happening here. Grazing occultation and the fact you've got a steep drop on one side and a slow rise on the other will be tied in with the specific geometry in the shape of the asteroid. And I don't think we Oh, there is a shape model available for it. That's one shape model. And there's another shape model. And if I take that up, then what do I need to do? I need to move that up there. You can see how that chord there is running very parallel to the edge of that shape model.
Yeah, very interesting.
Yeah. These are the things we can, the tools we have available to investigate the light curves and the overall circumstances of the event. And I'll be showing a bit more of that this afternoon with the binary asteroids, including an example where this type of thing essentially ruled out an observation as being a binary asteroid.
Thank you very much, Dave.
Yep.
Okay, if there's no more, Dave Galt, did you want to say something very quickly? No? That's right. Lunch is served for us here, so we're going to break now, returning at 13:20 Australian Eastern Daylight. So it's about 45 minutes or a little under. So yeah, thank you to all the presenters in that session. Quick round of applause, virtually and physically.
Can I ask a small favour? I've just changed the batteries in that mic that was causing problems earlier. Can someone let us know if the audio sounds better? Sounds better in this room already.
Yes.
Can I confirm? It does sound better?
Yes,
Yeah.
that's much
That mic's probably still working. Just the old batteries. Tough.
Yeah, good.
Thank you. Talk to you later.
What's for lunch?
I don't know. I haven't got there yet.
Ah.